Welcome to those who just joined. We're just about to get started, so please sign in to the notes document. And yeah, let's go ahead. Brianna, take it away.
Yeah, thanks, Amy, for organizing. I'm going to share my screen. Hopefully you're seeing the slides. But yeah, good morning, afternoon, everyone. And yeah, thanks for the invitation. I'm going to be giving, honestly, a pretty high-level overview, no more than, I think, 10 minutes of just what the current status is for our GeoZarr steering working group. I'm going to be calling it a SWIG. So our overarching goal is to try and get a geospatial spec adopted for Zarr. And I know that this is part of a 3-part series for Zarr-related discussions, so I'm not going to go into a crazy amount of details on Zarr itself, but I do want to provide some more context, just sort of a timeline of how we got to this creation of a GeoZarr SWIG. So Zarr itself was created back in 2015 as just a more simple hackable data format for n-dimensional arrays. The initial implementation was in Python, but now it's implemented in many different languages. And it is a community model, which is led by a really awesome person, Sankeet Varma. Not sure if he's on the call, but he does a great job of organizing Zarr efforts. And what makes Zarr a hackable format is the same characteristics as to what makes it an ideal cloud native format. So it's the idea, right, that you can take a cube of data, chunk it in a meaningful way, and then map a desired selection of data to those chunks. So again, that was all the way back in 2015. Fast forward to 2022. A GeoZarr draft was proposed by Christophe Noël from an ESIP project. He's currently at Spacebell. And the genesis of this was a need for a cloud native database. And initially they were experimenting with cloud optimized geotiffs or COGs, but they realized that was not enough. They had extra dimensions. They quickly realized that zarrs would be a more ideal format to consider. But when the switch was done to zarrs, they realized pretty quickly that common libraries like Xarray, GDAL, etc., needed some additional geospatial metadata to actually make the zarrs work. And so this resulted in Christophe creating a first draft of GeoZarr and really focused on the use of CF conventions and really an implementation in CF. A few months later, Zarr itself, so not GeoZarr, Zarr as a data format was adopted as an OGC community standard. And just a definition of what a community standard is, it's an official position of the OGC endorsing a spec or a standard developed external to the OGC process. So I want to make this distinction between Zarr itself becoming a community standard, Zarr 2.0, versus what we're really focused on today, which is GeoZarr. This brings us now more currently, so a few months ago, representing one of the data centers at NASA, we are interested in using zarrs and also making public zarr stores. And as a data center, we're obviously very focused and concerned on metadata standards, specifications, etc. So the question comes up of, okay, we want to use zarrs. What sort of metadata do we need to store in those files? I had reached out to the Zarr community, got connected to Ryan Abernathy, who referred me to the OGC community standard, but then also highlighted the GeoZarr efforts from Christophe Noël. And we've started picking up this conversation of, okay, well, clearly there's going to be a need for an OGC adoption of a GeoZarr spec. What can we do to sort of move forward this process? So that brings us to today. And since then, we have moved the initial work from Christophe to the Zarr developers GitHub repo. You can sort of track lots of ongoing issues, etc., in this link here for the GeoZarr spec. Giving a bit more context and motivation of then why a SWIG and why now. Again, zarrs are increasingly being used for geospatial data archives. And so just representing one data center, we want to understand what metadata is required before we start massively producing or making available zarrs. There's still tons of open technical questions, which I'm going to spend quite a bit of time right now talking of where we've gotten kind of stuck a bit as a SWIG, And there's clearly a need to work out more interoperability use cases using Zarr data formats and common libraries. So the SWIG so far has been a total open process. Anyone can join our meetings. This is not something like we've elected people. I've just listed sort of people representing different companies that have regularly been attending. So we have people from ESA, Spacewell, NASA, Earthmover, USGS, DevSeed, Carbon Plan, Planet, and Element 84, pretty consistently coming to our bi-weekly meetings. Obviously, we'd love to get more input and voices. So if you're interested in joining, you will see all the information at the end of the talk. So when we first joined together in January, we took a meeting to just try to write out different use cases. And we were explicitly doing an exercise like, I as a data scientist want to open a Zarr store, in Xarray and visualize it, or I want to be able to open a Zarr store in a web browser and visualize the data. I want to be able to do time series analysis. And in writing out those use cases, we came up with more higher objective goals of like, what is it that GeoZarr needs to accomplish. So it's very clear that we need easy compatibility with existing popular tools like GDAL, Xarray, ArcGIS. We want Zarrs to help users discover, access, and retrieve data. That includes subsetting it or potentially other versions of a data collections that are rechunked in different ways. We want to be able to use GeoZarrs to combine different types of geospatial data, so weather models, satellite images, digital elevation models, etc. We want to be able to have Zarrs create and display geospatial data in web browsers. And lastly, we want them to support serverless, cloud-native data analytic patterns. So these are all great higher-level objectives, use cases, etc. But when we started actually having conversations of how we're going to do this, it became very clear that we were getting put in the between two communities, the sort of GeoTIFF metadata community and NetCDF CF convention metadata like communities. And I believe Ryan Abernathy is writing a blog post on this because it's actually a really fascinating conversation of trying to get sort of these two worlds together. But I've listed a few open issues to highlight really where we've been having crazy in-depth conversations, very interesting conversations, but it has been a bit of a roadblock to move forwarding the GeoZarr process. Just for example, it was even highlighting, what is the difference between sort of the CF data model and a NetCDF, the CF data model and the NetCDF data model, where NetCDF data model really sits on top and is a more flexible version of CF conventions itself. And how is that relating to now Zarr, right? How are we going to implement that if we want to in Zarr data format? It also started posing questions of, do we want to then improve CF conventions itself? So for example, integrating CRS, coordinate reference system type information. If GeoZarr spec currently is adopting CF conventions, and we're saying that CF conventions are not enough and that they need things like CRS to be considered, what would that look like? And what is that process going to be? What additional specifications are sort of needed to be put into GeoZarr that work currently for GDAL, for example, transforms or other spatial coordinate variable support systems. This is all to say that these are really interesting technical questions, open-ended questions, but it's not necessarily GeoZarr's focus to solve those questions, right? We really want to push forward adopting this as a specification. And if we're realizing all of these technical potential issues, we think both of those can keep being moved forward in parallel. And I definitely want to make this a bit of a call to action if this is interesting for anyone on the call to come help us address these bigger technical issues on its own while we continue to move forward the GeoZarr into an adoption of like an OGC type process. So GeoZarr as it relates to a Zarr convention. So currently there is a fourth ZEP that is formalizing the concept of Zarr conventions. which would allow communities that have more specific like domain data model needs to get support in ZARRs. So this is not official, but this would allow us to not have to follow the ZEP process itself. Instead, we would use the convention process that's proposed by ZEP the fourth ZEP, to be able to put a data model out there for geospatial needs in ZARR. And last thing of where we were at in the OGC process. So initially we were debating between whether GeoZarr should be a new community standard, so really being developed outside of the OGC process, coming from the community itself, or going through a standard working group. And there was initial hesitations of going through the standard working group, just potentially for bureaucratic reasons, not sure how long this would take, what sort of effort, and if we could get a big momentum in the community to push this forward, it might be easier and more lightweight to do the community model. But because of all those open-ended technical questions, to be honest, we've been making pretty slow progress so far. And so right now we're leaning towards going with the standard working group process, while trying to in parallel address those technical issues, trying to understand that interface again between GeoTIFF and NetCDF worlds, etc. So yeah, lots of open questions, lots of work to do. I'm kind of ending this again as a call to action. If you're a producer or a user, or you're interested in ZARRs in general, we definitely could use people's help really in the coding and implementation aspects of this. I'm posting the links of all of our past notes here, how to join future meetings, the open repo on GitHub, and just a lot of kudos to Christophe Noel for putting together the first GeoZarr look, and Ryan Abernathy and David Blodgett for really pushing these really interesting conversations. And if there are other SWIG members on the call, I happily defer if they want to add any notes, and yeah, take questions. So thanks.
Awesome. Does anybody have questions for Brianna? I have a few, but want to open it up to the group first.
Yeah, I could ask one. I remember like a long drawn out discussion in the CF group about including CRS WKT. Is that? And I thought I got merged in with the, but I don't know. Maybe we don't want to go down that rabbit hole here. But did that not happen, or what happened there?
I don't know the status of that, and I just warning that it is probably a very big rabbit hole. I'm not sure if Ryan or someone else has more background on that than I do, but we definitely get caught up in those types of discussions a lot, and it seems like we get roadblocked on other outstanding issues like that. And again, it comes back to, is ZARR really the appropriate place to resolve those issues? Sort of like why would it be on GeoZarr's shoulders if that's still something, an open-ended question on CF conventions and maybe limitations of CF conventions.
Right.
So,
I guess if CF refuses to budge, then what do you do? I guess, right? Like, yeah.
Yeah, that's definitely my interpretation. Like I've been pushing to scope this very narrowly in the sense and say like we can't fix all of the metadata problems in geospatial world. We can't resolve this decades old sort of duality between CF versus sort of GeoTIFF or GDAL data models. Yet it seems hard to accomplish our goals without at least sort of picking a horse there. And so my impression is it would be really helpful for us to have more people involved who are familiar with those upstream standards and communities, like people from GDAL, people who, David has been really helpful because he's really enmeshed in CF world, but figuring out the right path here is hard.
I agree with you, because I think David was sort of like a lone voice in the CF land in a lot of those discussions, and kind of beaten down by the CF community who didn't really understand the importance of trying to get coordinated with GDAL.
Tyler, do you want to go ahead?
Yeah, could somebody just give even a short summary of the CF community's reluctance? Is it mostly that the models or the data sets they deal with are geographic coordinates and so they don't see the value of CRS? Or like, is it an outlier for them that they don't have to worry about most of the time? Is that the reluctance of including it?
The CF response generally tends to be, why would we make a special case for something that is already covered by our more general data model? So like, for example, like to get real specific on like what is the main issue? It's how do we describe the coordinates of like a raster image, right? Like, and in GDAL world, it's like origin, offset, transform, right? It's like really simple, right? And in CF world, it's like we have like CF coordinate arrays, and we have, you know, explicit dimensions where every point is given a coordinate. And, you know, whenever someone goes to CF and proposes, why don't we allow for something simpler and more lightweight, they'll say, well, this is a subset of what we already support. So why not just use the existing, you know, CF conventions? Why do we need a new extension to the convention to cover this like more narrow, more specialized use case than our extremely general data model? And that's where the discussion tends to break down, because people say, well, it's more efficient to do it this way. And they say, well, that's not our priority. And there just doesn't seem to be a mechanism to converge on that.
I find that kind of interesting, because CF, I view the value is that they made a special case of the general like netcdf metadata. They actually made it useful for a lot of people. So why would they be resistant to yet another special case that is very useful for a large subset of users?
Tyler, I believe there's almost no one better equipped in the world than you to actually like resolve this. Like, if you wanted to actually take this on, and you know, it just takes a lot of like talking to people to convince them that the way other people do it is not stupid, right? And it, you know, few people have the credibility in both communities and the experience with both in both worlds to navigate that. But you're one of so trying to nerd swipe you here.
I'm interested enough to like learn more and attend spec meetings to understand more of the issues that are blocking it. Yeah.
So with respect to the spec, I mean, there in the GeoZarr spec that was put out already, there are some specifications, right? There's a document out there. So of the content that's in there, like what is sort of up for debate, do you think? I'm wondering, you know, you talked about the scope of this thing. Can it be that in scope is just sort of revising what's there?
Yeah, so what's there is the CF convention essentially itself. And that's kind of, I think, the easiest default, right, is moving forward with CF, and then where these like long-standing issues of should CRS be integrated and things like that is sort of a note aside. But yeah, no, Ryan.
Well, a really practical issue with what's there now is that like GDAL can't read it, right? So like if we really want to have interoperability and have a spec for geospatial data cubes in Zarr that is readable across the ecosystem, it needs to work with GDAL. For GDAL to be able to read it, GDAL ideally wants a specification that says, here's how you know, the metadata are encoded. From what I understand from talking to Evan and the GDAL maintainers is that all of the CF coordinate stuff is very much special case to the netcdf reader in GDAL. Like, it's not accessible outside of, you know, like it's not accessible from the Zarr reader. So it's like a heavy lift for them to like refactor GDAL to be able to apply CF coordinate conventions to non-netcdf data. And so if we're asking them to do that, like we should be like pretty confident that that's the right way to do it. What GDAL would clearly prefer is to use like origin, offset, transform style encoding of the CRS. And if we could instead find a way to put that into the Zarr, which is like easy enough to do, you just stick it in, but then it's like, okay, now these Zarrs are not CF compliant anymore. So it really does matter when you're asking these implementations, particularly like the geospatial ones. Like, we would like to open Zarrs from like QGIS, right? Like, we'd like to open Zarr like God, even like ArcGIS, right? Like, but we need to like really be clear about like the CRS issue before
Okay.
asking them to do work to support that.
Yeah. Okay, thanks for breaking that down. That was helpful. Okay, any other questions for Brianna? Awesome. Well, I'm sure you will get some new attendees to your spec meetings, it sounds like. All right, let's go on to Norman. Norman, are you ready?
Yep, I am. Let me share my screen. Okay. All right, yeah. So I wanted to talk about sharding today. First, a few words about myself, because I think many people know me in this audience. So I'm co-founder of Scalable Minds. We are actually in the bioimaging domain, so I'm kind of an outsider to this meeting, but I think sharding might be very useful. So I think it's interesting to talk about these things. I'll first spend a bit of time on like the tools that we developed, just so that you get a context of why it matters to us, and also so you can see some of the cool tools that are available in the bioimaging space. And then in the second part, I'll talk about sharding in more detail. So one of our products is WebNozzle, which is an open source tool for visualizing very large data sets. So we focus on microscopy images. This data set, for example, has a resolution of, I think, 4 nanometers in XY, and in Z it's a bit thicker. So even very tiny volumes, less than a cubic millimeter, can get very big. So this data set, for example, is 50 terabytes in size. And WebNozzle is a tool to visualize these kind of images. And you can also use it to annotate them. Here's a segmentation that we've loaded in, and you can see this pretty neuron popping in the lower right-hand corner. So you can really work with them and generate these kind of segmentations. There are automated tools and manual tools. This is a manual one, and there's some features in there as well that makes it very easy to work with 3-dimensional data, because that's kind of where we focus on, and try to make the lives of the scientists easier to work with this data. And then because everything is in the cloud, it's very easy to share data, and I'm sure that many of you know how this works. So you can just send a link to some from WebNozzle, and your colleagues that can be around the world somewhere will be able to see the exact same data and the exact same screen as you're looking at. So you could use this to then collaborate very, very closely with each other. What it does under the hood is basically it uses Zarr for all of the data needs. So it can connect various sources. And in the bioimaging space, the most popular one is like an HPC, where they have dedicated institutional storage systems where they store these large data sets, but more and more the cloud is also being used. And you can feed this all into WebNozzle, where you can do visualization. You can also manage these data sets. You can do your annotations, set access controls, metadata, and all of that good stuff. And then from there, you get a unified Zarr interface, so that you can share that with other people. You can, again, do processing that could be in an HPC or in a cloud environment, and you can visualize it and everything. So WebNozzle is really like a central hub for managing all of this data, and then using it downstream in various different kind of applications. So this is a use case that it happened very recently, where we had a lab in China that acquired the images, and then they were annotated in South America, analyzed in Europe and in North America. And then after they've been published in a journal and they include links to their data in WebNozzle, they were then able to, basically anybody in the world was then able to access that data and explore the figures interactively on top of that. So that's WebNozzle. Our other tool that we do is automated segmentations, in particular for new writes. So again, we have data sets that are like half a petabyte in size, just a single 3-dimensional image. And then the idea is basically to reconstruct all of these beautiful neurons that are inside of this tissue volume, and try to find all the synapses so that you can basically figure out how the connections inside of these neurons are. And that's a deep learning powered toolbox that we developed and is in use in neuroscience today. So now let's talk a bit about sharding. Why is this important? And for our web nozzles in particular, it was a key enabler was that we had chunked three-dimensional data stores, so that we basically take this volume, chunk it up into smaller chunks, and then be able to stream that directly to the browser. So when we started developing web nozzles 10 years ago, that was our approach to solving this issue, and we came up with a chunk size of 32 by 32 by 32 voxels, which is very small. Typically, our data is in 8 bits, so that would give you 32 kilobytes per chunk. And now if you do some math, this gives you a ton of small objects very quickly. Even a terabyte in size already is 33 million files. And storing this on file systems is not really a good idea, because then you run out of inodes and directory listings takes forever and all of these problems. So eventually we solved that by just putting multiple chunks into one file. And that's essentially what sharding is. So you divide up all of your data in the chunks that are useful for you, but then you just store them in larger containers. And I'll talk a bit more about the ups and downsides, how it can help you and how it can also hurt you in a bit. But that's a general idea. So if you can just think of sharding like you have a large file, you put in all of your chunks in there, and then you have some sort of header or index structure that basically gives you directions where to look for each individual chunk in this particular file. And the way we implemented this for web nozzles was that each chunk would need to be read in one sequence, because most file systems run on spinning disks. And if you can do a sequential read, that's actually quite fast. The other requirement that we had is that each chunk needs to be compressed individually, so that we can compress them but still be able to read them individually. And then the other thing that we use that is quite interesting in terms of performance when working with these kind of data is that we stored all of these chunks in Z order. So Z order is like a space filling curve. So chunks that are in close proximity in three-dimensional space are also in close proximity then on the disk. So when you linearize out the ordering of the chunks in the file, then you can basically be able to, with one large sequence, read a bunch of chunks that are close by. So that's very efficient if you want to read a bunch of chunks at a time. And yeah, that was basically the implementation that we did for our web nozzles purposes, and it was like 5 or 7 years ago. And there are a couple of upsides to this. For the first part, well, it solved our problem, so we got rid of these exploding numbers of files. We could reduce it down, but it also brought a couple of new challenges, in particular when writing to this. So in this particular, parallel writes get a bit more complicated, in particular if you're working with compressed data, because then you have variable chunks in terms of like how many bytes they consume inside of this file, so you never know where to place them. Working with uncompressed data, that's very easy, because the byte offset can be known a priori. But if you have compressed data, then they might be anywhere, just because you don't know the byte lengths of all of the chunks ahead of time. So essentially, if you're working with compressed data, this requires you to work to write out one chart at a time. So whereas a chunk is like the level that you can read at, because they're compressed individually, a shard becomes the unit that you write once at a time. So it's kind of this 2-level hierarchy that now becomes apparent when structuring your data. So as I said, we've been working on this for quite a few years now, and now the bioimaging community is also moving more and more into Zarr land. So of course, we wanted to be able to use this cool feature also in Zarr, and we figured out there was nothing there. So we were thinking about how could we make this happen. And the idea is basically to implement sharding as a codec. So you can still think of your data that is an array. You chunk it up just as you do normally, And then there's another layer of subdividing these chunks, and then and this essentially then become your new chunks, and the other chunks, the old chunks, become your shards. So that's terminology gets a bit weird, which is why we now call these outer things shards and the inner parts chunks. Yeah, and it's the same idea, right? So you have these shards, they become your unit of how you can write stuff. If you're using compressed data, and your chunks are the unit that's the smallest unit basically that you can read out at a time. So just a couple of technical details of how the binary shard format for Zarr works. So you have this binary object, which you can store then just like you would store the regular chunks. But there's some metadata encoded into this. In particular, there's this index which is appended at the end of the file. And putting it in the end of the file is useful because then you always know where it is. So it's always going to be the n last bytes. And when working with cloud storage, for example, you can request to get the suffix of an object. So that's quite handy. So you can just tell like S3 to give you the last 1000 bytes of an object, and then that could be your index. And you know how big the index is depending on the chunk shape that you set in the Zarr metadata. So that's always the last part. And then the rest of the file is made up of all of these chunks. And actually, the thing how we implemented or are proposing it now is that there's no predefined structure how you need to structure this or where you want to put your chunks. So they can be in arbitrary order somewhere in this file, and that has some nice properties. So first of all, the application that writes these shards is in charge, and they can apply whatever ordering they want. So for us, again, the C order or Morton order, same thing, different name, we can just do. But anybody else could just do like a regular C order, or just do random shuffling of chunks if that is useful for a particular use case. Also, you can just leave out chunks. So if there's no, if you don't have any data for a particular chunk, then you can just leave it out, and that would be the same as if you would just not store an object for this particular chunk in a regular Zarr. And then the only penalty that you pay is that basically you have like two. So 64-bit numbers that you waste basically in terms of storage space. So that's not a huge price to pay. You can also leave arbitrary gaps in between chunks, and that might not be a useful idea just from looking at it, but these gaps could actually contain some metadata that can be useful for other applications. So for example, this would even allow you to use HTML5 files as your shards, because HTML5 is fine if you just append stuff at the end. So you can put your index at the end, and then all of your chunks could be like individual data sets in this HTML5 files network could also work. So you could even use these different tools. And if you have an underlying system, a storage system that allows for appending new stuff, then you can also have an append-only workflow where you write out a chunk, you add the index, and basically everything is empty except for this one chunk. Then later on, you write the next chunk, and you append now a new index, and you can basically do this one step at a time. And again, that might not be useful for every use cases, but for some use cases, for example, in microscopy land, it can be very useful when writing out images as they come from the microscope. So you go one section at a time. You could write out a chunk first, put in the index, and write the next chunk, rewrite the index, and append it again. So this can be useful for some use cases. It's not super efficient because you might have you will have duplicates of the index in your file, but if that might be an okay price to pay if each of these sections is a couple of gigabytes in size, for example. So that's how we're proposing it. There is a ZEP out there if you want to know all of the details. From a user perspective, it's basically just another codec that you can add to the JSON. Probably you won't do that by hand, but you'll do that by writing it by using a library. and setting it up. So yeah, and the ZEP2 is ready for review at this point. It depends on ZEP1, which is about Zarr v3, what I think you heard about in the last meeting. So that's currently under, like it's in the approval phase. So we're waiting for feedback on ZEP1 so that Zarr v3 can get approved. And hopefully that's gonna be happening in the next month. And then after that, we'll ask the council again for ZEP2 to be able to incorporate feedback in there and to get that approved as well. So it's in terms of the drafts, it's pretty far ahead. I wouldn't expect too many changes to the specification at that point, but we'll see what the feedback from the implementation council will be. Yeah, and if you so the ZEP is at this URL, and the draft specification is at this URL, and I'll put them in the notes and also link my slides there. And if you want to try it out today, that is possible. There is an implementation of Zarr that I created. It's highly experimental, so it's I wouldn't recommend it to use it for any production use cases, but I think it's great now just to get some sample data sets. It implements the current version of Zarr v3, and it also includes the sharding codex, so it can be used basically to generate these data sets. It's not developed with performance in mind, and it also doesn't have all of the interoperability capability that Zarr Python has. So it's not really meant as a drop-in replacement or anything, or even as a serious replacement, but it's really just meant to play around with the new specifications and yeah, get some feedback on the process. If you're looking at Zarr Python and looking through the code or documentation there, then you might also find a version of sharding, but a word of caution there, that's a version that's a bit older and it doesn't reflect the current status of the specifications. So there needs to be some work to put into Zarr Python to be able to work with Zarr v3 and also the sharding specification. All right, so thank you very much. You can find me on Twitter, myself, on LinkedIn if you want to stay in touch. And yeah, if you're interested in playing with some bioimaging tools, then feel free to try out webnozzles on webnoz.org. Thanks.
Awesome. Yeah, that portal looks really cool. I guess I'll start off with one quick newbie question because I'm not as familiar with like the imaging work that you're doing. So with your Zarr data, is that, or so with geospatial data, right, the coordinates traditionally usually are like latitude, longitude, and time. So with your data, is it usually just like the pixel location, or do you have like standard coordinates for that type of data that you're working with?
Yeah, so there's actually a wide variety of coordinate systems that are used. Like if you work with a microscope, typically the thing that you get out is a two-dimensional image, but this might have also channel informations attached to them. So that's already three-dimensional. Then if you have multiple sections, or if you work with an MRI, then you also have three-dimensional data. And then again, adding a channel on top of that becomes 4D. And then if you have a time series of this, then you can get 5D data, and that's basically where bioimaging typically tops out. So and yeah, the way that the data is addressed is typically by just having a fixed grid, and yeah, then you have a fixed physical some fixed dimensions that are attached to each voxel. But I mean, I was just listening to your discussion about the CF model and a coordinate system. So that's also something that is happening in the bioimaging space at the moment, because of course the truth is that actually the microscopes don't acquire everything on a precisely fixed grid. So there might be some noise to the grid itself, and for some application it might be useful to capture that. So yeah, but there is some metadata, and it's so there's the open microscopy environment, OMI, and there's OMI Zarr. So there's some metadata on top of Zarr to actually specify all of these coordinate systems and transformations. So it seems like it's a similar thing to what you're working on with GeoZarr.
Yeah, it'd be interesting to learn more about the similarities and differences. If anybody's like, it sounds like you're probably one of the most knowledgeable people in both to talk about them. But Hey Lang, do you have a question? I can't hear you here if you're speaking. Maybe you want to type it or check the audio. Does anybody else have a question maybe while we wait for Hailing to test out her audio? Looks like she might be rejoining. I guess, let's see. Do you guys use, what type of thing do you use to catalog your data in the field that you work in?
So I think there's like two worlds in bioimaging. The one world is labs that work with very large data sets, but only have like a handful of them, and they don't care too much about cataloging that data up until they publish data. And then there's this other world. They basically have many thousands of tinier data sets, and they use image data management systems. So one of them is WebNosis, another one is Omero. And there are a couple of others that people use. And there you can attach all sorts of metadata to the images then. And yeah, and for purposes after publication, there are a couple of data repositories where you can submit your data to. And when you do that, you get like a DOI, and you can attach some metadata to them so that people can find it again. And it's still early days, I guess, in terms of Zarr adoption. But more and more of these data repositories also get Zarr enabled, which is great because then people can actually access these data sets in a streaming-based fashion, which makes it much more plausible that people will actually do that, because otherwise who would download like hundreds of terabytes data set just to look at it or do some simple analysis on top of that.
Yeah. And you said in your bioimaging field, there are different types of coordinate systems that you guys are trying to work with?
Well, not necessarily different. I mean, so the coordinate system typically is like just you have a fixed grid, as I was mentioning, and then you have like physical units attached to each dimension. That could be like a space or time or channel dimension. And but there are like different transforms that you can do. Can be simple affine transformations or displacement fields or spline-based stuff. So that's typically what we use.
Got it. Hailing, did you want to try, oh, sorry, Hailing, it's, would you like to try your audio again? Hi, Liang. Oh, it looks like we're waiting for. I guess, Ryan, have you gotten a chance to try out the Zarita library?
No, I've just been looking at it.
Okay.
We have a lot of work to do in Zarr Python to bring it up to spec. This is something the community needs to figure out how to deal with.
Yep. Okay, cool. Let's see back. Okay. Waiting for Hai Liang as well.
If you're waiting for me, can you hear me now?
Yes.
I can, yes.
Okay,
Great.
yeah. I'm not sure what happened. Okay, so very nice, stuff, Norman. So, question for you. Like, I have two questions. So first one is kind of related to what Amy asked. Like, basically, like, we have like, let, long, and time, and you have like your 3-dimension, right? So, and I think basically, each slice the resolution is fixed, but along the between different slices, depending on the like how laser cut the brain, right? So like and it could be like very thin, very large, or like who knows. But in terms of the chunking, so each chunk, like for example, like for us, like we are trying to make the chunking along different dimension to be balanced between different dimension too, so we can have a like optimal service, right? So for your application, I believe the chunking along the third dimension, which is like how do you cut your the tissue, right? So that one, the resolution will decide like how long that dimension will be, right? So my question is like when you decide on the chunking, like for each chunk, and for the third dimension, does that be the performance wise, will that be optimal if you do some optimization along the chunk dimension or the shard dimension? Which one is more important, chunk versus shard?
It's a very interesting question, but actually we just use uniform chunk sizes. So we just chunk up the data, and we still use the 32 by 32 by 32 chunks for 3-dimensional data, and then we package them all up in a shard that again has 32 by 32 by 32 chunks. So that comes out at like 1,000 voxels cubed. And that's basically what we work with. And we haven't worked with different chunking schemes to date. I know that some other folks are using different ones, but I think like they also just use uniform or like cube sized chunk shapes.
Okay. So basically it's equal. Okay. So which one is more important? It's like so I believe the shape will be different between shard and chunk, right?
Yes.
Okay.
Yes.
So we are talking about the chunk level. The shard level matters, right? So basically, like each shard will have many chunks, right? So how many chunks there will be along each dimension? So what will be the consideration in terms of the performance? Like, is that very important? Okay, so basically what I'm thinking is like us also, like, right? So we have our 3-dimensional data, right? So, and we may want to organize into shard, and what will be our consideration, like what we should keep in mind when we design, like the sharding shape?
Okay, well, that's a good question. So for us, how we like to think about it is like the chunks, the inner chunks, that size is determined by how we want to access the data. So for us in Web Nozzles, this is how fast can we load that data? Like if you remember, like the data is orthogonally cut. And we need to fill up the screen, so we need to load the data. And the smaller the chunks are, the less waste we have basically in terms of how much data we download. And if the chunks are bigger, then we have less like network operations, but we have much more pixels that we actually download and don't need. So that's that consideration. So that's the read use case. And the shard is determined by how we write the data. So because in ideal world, we always want to write a full shard in one go. So that's determined by how much memory you have on the system, how much, and how it makes sense. So for a microscopy use case, typically we acquire the data in sections, so that will be one section after a time. And then we do a rechunking to be able to transform this in these 3-dimensional cubes. So that's a step that we almost always do. And then we, and I mean, for us, and then it's a balancing act of how many objects you want to have in the end, and how big of a shard you can keep in memory at a time, or work on to do useful stuff. And that's where, for us, like this 1 gigavoxel felt okay-ish, because the number of line nodes were then manageable, and that's something we can keep in RAM, and we can even keep in VRAM if we want to do deep learning applications, stuff like that. So that's the number that we use, but you can also go bigger or smaller depending on use cases.
Okay, very cool. Thank you.
And in the Zarr spec, it's very flexible, so you can pick whatever you want. The only requirement is that you need to have You can only have like full chunks in a shard, so it needs to be divisible.
Yeah, I mean, like when this is like really, you know, in V3, so like I know it's like really okay. So eventually that's going to be optional, right? So we don't have to use the sharding. So
Yes.
if I, okay, so it's optional, which means we, you know, is that going to be like something just purely transparent to the end user, which means internally they are, you know, we are not requesting for sharding, but will they still like consider each chunk as a shard, then add a header to that chunk, or like no, totally there's no separate object for the head?
So for the end user, I mean, it obviously depends on the library implementation. I think in Zarr Python, it will be like a codec that you configure if you want to create a new array. If you're just going to read it, basically it will be fully transparent. You're just going to open the thing and the Zarr library will take care of it. But then again, because for writing the data, it might be worthwhile to the end user to think about how the data is actually structured in the underlying structure. So because if you then start and write single chunks inside of a shard file, that might lead to suboptimal performance, because basically what you need to do then is download the whole shard, write out a new shard with this updated chunk and pass it back on. So that becomes a big performance penalty. But if you know that you're working with a sharded data set, then you could optimize that and basically try and write out full shards at a time.
Okay, all right, cool, thank you.
Awesome. Thank you so much, Hailiang and Norman, for that discussion. Anybody else have questions for Norman? Cool. Well, I want to thank Brianna and Norman again for joining us and being flexible with your schedules. So yeah, thank you so much. This really interesting topic, really exciting stuff to see this all moving forward. So thanks again, and I look forward to the next one and seeing where these both go. Bye, everyone.
Thanks,
Thank
bye.
you.
Thanks,
Thank you,
everyone.
guys.
Okay, bye.